Hi guys, it's Dr. Bay and here's Bugsy, and today we're going to go over part 2 of pericyclic reactions, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the 7 seas, learning about spectroscopy. Organic chemistry.
Recall that every alkene is made up of one pi bond and one sigma bond. Carbons that make up an alkene are sp2 hybridized, where two atomic p orbitals mix or mathematically combine to form pi molecular orbitals, and these are labeled as wave number 1, 2, etc., starting from the bottom and increasing in energy going upwards. Since the molecule ethylene contains 2 pi electrons, we're going to fill the MOs with 2 electrons in the lowest energy MO. MOs that contain electrons are called bonding MOs, and the ones that do not contain electrons are called anti-bonding MOs. Now let's take a look at the MOs of a larger conjugated molecule. 1,3-butadiene is a conjugated molecule with 4 carbon atoms and 2 alkenes that start at C1 and C3. In order to draw the pi molecular orbitals of this molecule, first we're going to determine how many atomic p orbitals there are. Since 1,3-butadiene contains 2 alkenes, and each pi bond in an alkene is made up of 2 p orbitals, this molecule has 4 p orbitals in total. Then all of the atomic p orbitals mathematically mix to form an equal number of MOs, which is where the pi electrons reside in. Remember that p orbitals are atomic orbitals that are localized to specific atoms and are different from molecular orbitals that are associated with the whole molecule. But don't worry, you don't need to show any work for this part. Then in step 2, we're going to draw all of the molecular orbitals. Since 1,3-butadiene contains 4 carbon atoms, we're going to draw 4 MOs starting with 0 nodes at the bottom, which is lowest in energy. Notice that when an MO has 0 nodes, this means that all of the upper blue lobes or phases overlap with one another because they're all the same color. And same with the bottom green lobes. Then if you look at the second MO right above it, that is higher in energy, this second MO has 1 node in the center. A node indicates that the phases or colors of adjacent lobes do not overlap and is drawn as a dotted line shown in red. Wave number 2 has 1 node, wave number 3 has 2 nodes, and wave number 4 up at the top has 3 nodes and is highest in energy. Then in the last step, we're going to fill the number of pi electrons starting from the bottom going up. Remember that this molecule has a total of 4 pi electrons, and each MO can only hold a maximum of 2 electrons. So the highest occupied molecular orbital, or HOMO, is the highest energy MO that contains electrons, which in this case is wave number 2. And the lowest unoccupied molecular orbital, or LUMO, is the lowest energy MO that is empty, which in this case is wave number 3. Recall that a Diels-Alder reaction is a 4+2 cycloaddition, which means that the 4 pi electrons from the diene interact with the 2 pi electrons of the dienophile under a very high temperature. From a molecular orbital standpoint, this means that the HOMO of the diene interacts with the LUMO of the dienophile. If we take this example of S-Cis butadiene reacting with ethylene, let's first look at their MOs. The HOMO of butadiene is the second MO from the bottom, and the LUMO of ethylene is the second MO as well. To simplify it, let's only look at the HOMO and LUMO, which are called the frontier molecular orbitals. The pi electrons from the HOMO of the diene are added into the empty LUMO of the dienophile, and in this case, this is the case for every Diels-Alder reaction. If we drew out the mechanism of this example, we can fill in all three arrows to produce the cyclohexene product. But let's also number the carbon atoms in the reactants and product. From another perspective, we can orient the diene and the dienophile to better align the molecular orbitals, and the carbon numbers are still labeled there as well. The dotted lines indicate where the new bonds will be forming. Now if we fill in the HOMO of butadiene and the LUMO of ethylene, we see that the blue lobes between C1 and C6 overlap, and the green lobes between C4 and C5 also overlap. This means that both sets of orbitals match in phase and have bonding interactions. Now if we look at a 2+2 cycloaddition, we'll find that the reaction is unfavorable under thermal conditions, but the reaction works really well under photochemical conditions. And this can be explained with orbitals as well. Let's draw the MOs for ethylene reacting with another molecule of ethylene. Since they're the same molecule, we're going to take the HOMO from one and the LUMO from the other. Now let's only look at the frontier MOs for simplicity. The HOMO of ethylene adds into the LUMO of a second ethylene. And here's the mechanism for this reaction under heat. Two sigma bonds are formed between C1 and C3, and another sigma bond is formed between C2 and C4. And from another perspective, let's orient the two molecules to better align the MOs. When we fill in the HOMO and LUMO, the green lobes between C2 and C3 overlap to form a bonding interaction. But notice that the green lobe in C1 and the blue lobe in C4 do not line up. Since the phases are opposite, this means that this reaction is actually forbidden. So a 2+2 cycloaddition with heat is unfavorable because the MOs do not align. But if the same reaction is done with light, then the reaction can occur. But how does that work? Well, light excites one electron to move up to a higher energy MO, which means that we have a new HOMO for one of the ethylene molecules. If we take a look at the frontier MOs, the HOMO of the excited state of ethylene adds into the LUMO of the ground state of ethylene. An excited state means that light excited an electron, and the ground state means its normal MO that was not excited. Now we can draw the orbitals of the new HOMO of the excited state of ethylene and the LUMO of the ground state of ethylene. And now we can see that the blue lobes between C1 and C4 overlap, as well as the green lobes between C2 and C3. This means that both sets of orbitals match in phase and have bonding interactions, so a photochemical 2+2 cycloaddition using light is allowed. So to summarize orbital symmetry in cycloadditions, a 2+2 cycloaddition contains a total of 4 pi electrons and is forbidden under thermal conditions but allowed under photochemical conditions. And a Diels-Alder reaction contains a total of 6 pi electrons and is allowed under thermal conditions but forbidden under photochemical conditions. Now moving along with another type of pericyclic reaction, now let's go over electrocyclic reactions. Just like cycloadditions, electrocyclic reactions are concerted, also involve a ring of electrons moving around in a closed loop, and occur through a cyclic transition state structure. In an electrocyclic ring closing reaction, a pi bond is converted into a sigma bond between C1 and C6, while the remaining pi bonds move one bond over. When the new sigma bond forms, it actually creates a ring. Now, in the reverse fashion, an electrocyclic ring opening could occur where a sigma bond could break to form a new pi bond simultaneously while the other two pi bonds move one bond over. So, in order for a sigma bond to form in an electrocyclic ring closing reaction, there are two types of motions that may occur. The first is a conrotatory closure, where terminal orbitals may rotate in the same direction. Remember that in order for a bond to form, the same types of orbital lobes must overlap. So in this case, in order to do that, both orbitals must rotate in the clockwise direction for the blue lobes to overlap. And since they're going in the same direction, this is called conrotatory. On the other hand, a disrotatory closure is when terminal orbitals rotate in opposite directions. In this case, for the orbitals to overlap, one orbital has to do a clockwise rotation, while the other orbital has to rotate counterclockwise for the blue lobes to overlap. Since they have to rotate in opposite directions, this is called disrotatory. To understand how electrocyclic reactions work, let's look at the molecule's highest occupied molecular orbital, or HOMO. The MOs of 1,3,5-hexatriene are shown on the right. Since this molecule contains 3 pi bonds, this means that it overall contains 6 pi electrons, so we should draw in 6 MOs where the bottom MO contains 0 nodes, and we increase in the number of nodes as we go up. Then, after filling in the 6 pi electrons going from bottom to top, we find that the HOMO of the ground state of this molecule is wave number 3. So now that we know what the HOMO looks like, we can draw them directly on the molecule with labeled carbon numbers. But we can actually simplify this even further by only looking at the terminal orbitals that are involved in the forming of the sigma bond. This means that we only have to look at the orbitals on C1 and C6. Now let's determine what direction the ring closing occurs through. Since the orbital on C6 has to rotate clockwise and the orbital on C1 has to rotate counterclockwise in order for the blue lobes to overlap, this means that the rotation is called disrotatory. Let's look at a thermal electrocyclic ring opening reaction of cyclohexadiene. Even though the ring has only 2 alkenes, we use the HOMO of the product that contains 3 alkenes. This means that we want our terminal orbitals in the product to be the same, where the top lobes are blue and the bottom lobes are green. In order for that to form, we have to rotate each lobe in opposite directions, which is called disrotatory, and this gets us to our product. Electrocyclic reactions are stereospecific, which means that the stereochemistry of the product depends on the alkene orientation. For the following examples, predict the product of the following electrocyclic reactions. The position of the substituents at the ends of the conjugated system are where we need to focus our attention on. In this first example, the alkenes are both E-alkenes, which means the substituents are pointing in opposite directions. Then if we draw the terminal orbitals of the HOMO, now with the methyl substituents, the orbitals have to rotate in opposite direction for the blue lobes to overlap. Since it's a disrotatory rotation, this causes both methyl groups to rotate upward, which means that in the product, the 2 methyl groups would be cis to one another or drawn on the same bond types. So when both alkenes in the reactant are E, that means that the substituents in the product should be cis. In the next example, the top alkene is E, while the bottom alkene is Z. Again, if we draw the terminal orbitals of the HOMO of a molecule with 6 pi electrons, we get the following drawing. The orbitals still have to rotate in opposite directions for the blue lobes to overlap, but now one methyl is pointing up in the product while the other methyl is pointing down. This means that in the product, the methyl groups would be trans to one another, aka drawn on opposite bond types. Electrocyclic reactions depend on the conditions under which the reaction is performed, and these observations can be explained by the Woodward-Hoffmann rules. If the total number of pi electrons in a molecule is 4, then a conrotatory rotation will occur under thermal conditions, or a disrotatory rotation will occur under photochemical conditions. If the total number of pi electrons in a molecule is 6, then a disrotatory rotation will occur if under thermal conditions, or a conrotatory rotation will occur if under photochemical conditions. Now let's do an example. Predict the product of the following electrocyclic reaction. The starting reactant contains 6 pi electrons and is reacting in light, so we expect a conrotatory rotation of the terminal orbitals. Remember that electrocyclic reactions only focus on the HOMO, and since this reaction is in light, one electron gets excited to a higher energy MO, which means that the wave number 4 is our new HOMO of the excited state. But like we discussed previously, we only need to look at the terminal orbitals of the HOMO, since these are the ones that are making the sigma bond. So in order for the same colored lobes to overlap, they must rotate in a clockwise direction, which means it's conrotatory. Since both alkenes in the substrate are E-alkenes, this means that the O-phenyl and the ethyl substituents will be trans to one another in the product. So in summary, cycloaddition reactions rely on the HOMO of the diene and the LUMO of the dienophile to align in order for the reaction to occur, and its conditions, whether it be under heat or light, will dictate whether the reaction can happen. And in electrocyclic reactions, the Woodward-Hoffmann rules tell us what type of rotation of the terminal orbitals in the HOMO are necessary for the product to form.
Organic.